Okay, so we'll begin. So today we'll study a new kind of object called modules, and is to characterize some simple types of modules. And on the way, we'll also solve matrix equations over integers. And the aim of this whole talk is to prove what is called as fundamental theorem of finitely generated modules. So let's begin. So before we delve into the definition of modules, I'd like to have an informal discussion on why study modules. So when we consider a vector space, the set of scalars is usually a field. So that will be R or C. And it operates on vectors through scalar multiplication. So you have multiplication and you have addition. Addition between the vectors and multiplication between scalar field and the vectors. So we would like to generalize this by taking the set of scalars to be a ring uh, instead of a field. We want to generalize this by taking a ring. Module theory involves on transferring as many desirable properties of vector spaces as possible to the realm of modules over a well-behaved ring. For example, vector spaces have what are called bases, and we would like to check whether every module we come up with does it have a basis or not. In doing this, we want to have some structure on the ring. So we'll be taking the rings to be a PID. And it turns out that modules can be far more complicated than vector spaces. And for example, not every module has a basis. And one application is that, as we'll see, ideals and quotient rings are both modules, and several arguments concerning both may be integrated into a single argument about modules. And we'll also see another application in probably upcoming talks that um, you can study more about linear maps between the vector spaces using modules. So let's begin. What is a module? So let R be a ring. A left R module is a set M together with a binary operation plus on M, under which M is an abelian group. So basically M is an abelian group. And a map R cross M to M denoted by Rm. This is basically the scalar multiplication. And so we already have two operations here. One is scalar multiplication between the ring and the module, which is just an abelian group in the beginning, and addition between the scalars, addition between the module elements. So when we have two operations, we generally need some axioms. So basically distributivity axioms. So this map R cross M to M should satisfy three main axioms. So the first one is R plus S times M should be Rm plus Sm for every Rs in the ring and M in the module. Next one is the associativity. Rs times M is R times Sm. And finally, we need to have distributivity over this over addition. So it's R times M plus N should be Rm plus Rn. Further, if the ring has identity element 1, then we impose the additional axiom called 1m equal to m. So 1 acts on the module m, and 1m would be m. So generally, we'll take these rings to be commutative rings with identity. Otherwise, we would not want any pathological cases. So commutative ring with identity, and in mostly we'll consider modules over integers and modules over polynomial ring with coefficients in F, a field. Okay. So with vector spaces, you have subspaces, and here you have submodules. So let R be a ring and M be an R module, and R submodule of M, we always append R while talking about modules because we want to know what the underlying ring is. So an R submodule of M is a subgroup of N, a subgroup N of M, which is closed under the action of ring elements. So basically, it is a subgroup of the so M was an abelian group with addition plus with addition as an operation. So it has to be a subgroup of M, and it has to be closed under the action of ring elements. For example, like if we want to split this out, so we need to have, for every, if x and y are elements of M, then x plus ry should belong to N for every x y in N and r in R. So this is the definition of the submodules. So you would have if you're familiar with linear algebra, you would have seen a similar definition for the vector spaces also. So basically it is a subset of M, and if you just you can make a module out of it. That's what this is intuitively saying. So at this point, let's see two trivial examples. The first one is R module R. So basically you take M equal to R. So now the map R cross M to M, what does that become? It's just, this is just R, this is also R. So it just takes R, and it's just normal multiplication, R dash. So this is trivially a module also. If S is an ideal of the ring, then you can consider S as an R module. So one also has S a R submodule of the module R. So if your module is R, then S is an ideal can be taken as a R submodule. Or if S is itself an ideal, then you can consider S as a R module. For example, here M would be equal to S. So one example is, if D is an element of R, then the this is nothing but dr. So the ideal generated by the a single element D, principal ideal. So since this is an ideal, you can consider this D as an R module. Okay. So now we consider maps between the between two modules, and we want both the modules to have the same underlying ring. So let R be a ring, and let M and N be R modules. A map phi from M to N is an R module homomorphism if it respects R module structures of M and N. What does this mean? So R module structure would mean we have two operations. One is addition and multiplication. So let's see how what restrictions do we put on a homomorphism. So firstly, phi of x plus y should be equal to phi of x plus phi of y for every x and y in M. Next, phi of Rx should be equal to R times phi of x for all R in R and x in M. So basically, this makes phi into a linear map. An R module homomorphism is an isomorphism if it is bijective and we denote M isomorphic to N in this case. So bijection means it should be 1, 1 and it should be onto. So as usual, you would have seen in the rings and groups. So kernel phi, we denote it as all those x in M such that phi x equal to 0. And the image phi of M, we denote it, which is nothing but phi of x, x in M. So two observations here. Since you're already familiar with rings and groups, you would have seen this. So R module homomorphism is injective if and only if the kernel is just a trivial kernel, only 0. And it is surjective if the whole if the image is the whole of N. So you have you basically have phi from M to N. So we have this is injective if and only if kernel phi is just the trivial, and it's surjective if the image is N. So phi of M is also denoted by image of phi. So now let's get into some examples. The first example is what is called as free module of rank N over R. So what is this? Basically, it's just nothing but Rn. So here R is a ring, and we consider all the n tuples, that is x1 up to xn, with each elements from the ring R. So how do we define the addition? It's just component wise. So x1 up to xn plus y1 up to yn. So we denote this. We define this as x1 plus y1 up to xn plus yn. This would convert Rn into a abelian group. And then multiplication is also defined component wise. So R times x1 up to xn, this is a element in Rn. This we set it to be Rx1 up to Rxn. Sometimes I would like to denote this tuple notation with the general notation, the notation used in linear algebra, like this column notation x1 up to xn. So both are almost the same. So this would turn this would turn Rn into a module and an R module. It will turn into a R module, and this will this we call this as a free module of rank n. You'll know why we call this as free module of rank n in the coming slides. So this is one of the toy examples for modules. In vector spaces, you have already studied that any finite dimensional vector space is a free module of some rank over a field. So if any v, you know, if it's finite dimensional, then it should be of the form Rn for some n, or if the underlying field is R, or if the underlying field is C, it's Cn. So if phi is a R module homomorphism from Rn to Rm, then this I'm sorry, I denoted it with the T here. Okay, let's take it phi. So then phi v is actually multiplication by a matrix AV. So here what is the matrix A? It's a matrix M cross N matrix with elements from the ring R. So each element is a element of this R, the ring R, and this is V. If we take it as column vector, then this is nothing but the matrix multiplication. So every R module homomorphism between two free modules of rank n, it can be taken to be matrix multiplication, and we denote this range, the range of the if A denotes this R module homomorphism, the range would be nothing called ARN. I hope this is clear. So let's see another example. This is if we take the ring to be integers. Z, so we call it as instead of R modules, we call Z modules. So consider a module over Z. These are nothing but abelian groups. We'll show this. A module M is a Z module if and only if M is an abelian group. So how? Suppose M is an abelian group. How can you make it a Z module? Just by defining, let's say 1 times M. For any M, you just define it to be M. 2 times M, you define it to be M plus M, and so on. N times M, you can define it to be M plus up to M. So this is N times. So this would convert this abelian group into a Z module. Again, so how do we define minus N times M? So basically this is minus M up to M times N times. So you can check those operations; they'll still stay true. For example, let's say x plus y times m, it would be basically xm plus ym, because what does this mean? This means you add m x plus y times, and that is not that is the same as you're adding x times and then y times. So this definition would make m into a Z module. And similarly, if M is a Z module, then it is an abelian group by definition. So Z modules are nothing but abelian groups. So if so, we are generalizing abelian groups in some sense by studying modules. Now another example, we said in the beginning that another common ring to take into consideration is fx. So fx is a polynomial ring with coefficients in f. The f is a field. F a field. So we show that a module over fx is nothing but a vector space with a linear transformation T. So what do I mean by this is that if V is an fx module, then this corresponds to V being a vector space and T is a linear map from V to V. So this bijection would be given by the element x acts on V as a linear transformation T. So let's try to see how this works out. So given let's suppose in the beginning that V is an fx module. So in this case, what happens? So first thing is that you have this multiplication definition fx cross m to m. So in particular, what do we have is for any c in f, you can make sense of c times m, right? So this will go to cm. So for any c in f, you can make sense of cm. That means V is a f vector space. That is vector space with underlying field f. Further, what do we have? We have x times m. So we can make sense of x times m, xm. And because of the three axioms that the modules have to satisfy, what do we have? Let's say we have x times, if you have m plus n, these belong to the module, this belong to V. This would be xm plus xn, right? And then uh, yeah, so yeah, this one is there. And then we have x times any, if you have any c here, let's say c is an element in F, then c x times c times m is c times x times m, right? So the, if you would now denote t times V to be x times V, okay, so then these two things make t into a linear map from V to V. So that's what I said here. So given an fx module, you can take V to be a vector space, and with you already have, you also have, by definition you also have a linear map, and this linear map TV is given by xv. On the other hand, on the other hand, let's say let's say V is a vector space, V is a vector space, and T from V to V is a linear map, a linear map. So what does this mean? So now what I'm going to do is I'll define x times V, I'll define this to be TV. So then I'll be forced to define x square V as t square V. That means t of V, because this would be x of V. So I'm trying to turn a vector space V into a module. So then and so on. So I'll have to define x to the power nv to be t to the power nv. So any polynomial p of x, I'll define p of x times v to be, so if this is, let's say, a n x n up plus a1 x plus a naught times v, then this I'll define this as a n t n v plus up to a1 tv and a naught v. So this is basically p of t v. The polynomial p, now x is replaced by t, and that is acting on v. So uh, with a linear map and a vector space, you can turn it into a module. So again here, so how do you go from here to here? You define xv to be tv. So here to here we defined tv to be xv, and here we defined xv to be tv. So this is what I said. So what the general way to study, like how you can study more about the linear maps and in a vector space, is you can consider V and a linear map T, turn it into an fx module, and you can apply the module theory to get more information about the linear map T. Okay, so now let's go to quotient modules. Let R be a ring and M be a R module, and here N, let's take it to be a submodule. Then you can make sense of M over N. So M by N, you would from groups and from rings, this would be an additive abelian group, quotient group, and you would have all the left cosets of N. So that is x plus N, x in M. Now you can make M by N. So M by N is now a quotient group. So it's basically a abelian group. So how do you make an abelian group into a module? You introduce scalar multiplication. So how do you introduce scalar multiplication? We introduce scalar multiplication by defining R times x plus N to be Rx plus N, and this is for every element in the ring and every left coset. So this would turn M by N, this would turn M by N into a module. Now again, if we want to verify some basic property like R times x plus N plus y plus N, and this is, by definition, this is R x plus y plus N. Now since M is a module, M is an R module, this would be Rx plus Ry. Now since N is a submodule, Rx, this would be Rx plus N plus Ry plus N. So this verifies, this verifies one of the axioms of the this one. The others are also similarly verified. So now we can make sense of quotient modules, and this would lead us to the first isomorphism theorem. That is, if you have an if you have an homomorphism from M to N, then we have M over kernel phi is isomorphic to the image of the image of phi. So let us try to prove it. And the proofs would be similar to what you have done in groups and in rings. So what do we have? We have phi, an R module homomorphism between two R modules, M and N. So now we can, since we now let us make sense of M over kernel phi. I'll try to denote this by K. So what would be M over K? This is nothing but all x plus K, where x is in M. So I would now like to give another map, psi. Psi would go from M over K to the image, phi of M. So how would I define it? I'll define it to be x plus K goes to phi of x, right? So is this a linear map? Let's check. So psi of x plus K plus y plus K, what would that be? So by definition, this is x plus y plus K. And how I define the linear map, this would be phi of x plus y. And since phi is a R module homomorphism, this is phi of x plus phi of y, since it respects the addition between module elements. Now by definition of psi, this is nothing but psi of x plus k, and this is nothing but psi of y plus k. So similarly, psi of r of x plus k, what would this be? By definition, this is rx plus k, by definition of the quotient modules. Now by definition of psi, this is nothing but phi of rx. Since phi is a R module homomorphism, this R comes out, R phi x. And by definition of psi, this is psi of x plus k. So so we have proved that this is the given map psi is actually a R module homomorphism. So now let's show that it is injective as well as surjective. So we have, I'll write it again. We have psi from M over K to phi over M given by x plus K to phi of x. So it is clearly surjective, right? Because if y belongs to phi of M, the image, then you can have some x such that y equal to phi of x, and clearly y is equal to psi of x. So you have some element in M by K such that psi of that element would give you y. So psi is surjective. Now why is psi injective? So let's suppose that again, to prove that to prove the injectivity, let's try to find the kernel of psi. So let's suppose that psi of x plus k is equal to 0. So by definition, this is phi of x equal to 0. What does this mean? This means x belongs to k, the kernel of phi, because phi of x is 0. What does this mean? This means that x plus k, so since x already belongs to k, this is nothing but 0 plus k, right? Why? Because x minus 0 just belongs to k. So that means this implies that x plus k is nothing but the 0 element. The 0 element in the quotient module is 0 plus k. So this means that kernel of psi is just a trivial element, 0 plus k. So therefore, what do we have? So we have that psi is injective. Once psi is a so this would mean that psi is a isomorphism, and we have M over K isomorphic to phi of M. So this K was kernel of phi. So this proves the first isomorphism theorem, and we are going to use this theorem in quite 2-3 more proofs. So basically, whenever we have M to an R module homomorphism, we can always have this isomorphism M over kernel phi isomorphic to image of phi. Okay. So now let's see generation. So we want to define. We want to, like, just as we study primes while studying integers, we want to see if the whole module is generated by a few elements. So how do we define generators and let's see. So given n1 up to nk submodules of M, we define n1 plus n2 plus up to nk to be the set of all finite, the set of all elements a1 plus a2 plus up to ak, where ai belongs to ni. For any subset A of M, we denote Ra to be R1A1 plus R2A2 up to Rn An. So each Ri belongs to R, each Ai belongs to A. So you would have seen a similar definition in rings also. So basically, Ra is nothing but the set of all finite linear combinations of the elements in A by R. And uh, yeah, so it is important that you know this definition very well. So if A is a finite set, then we denote Ra by Ra1 plus Ra2 up to Ram. So this seems very intuitive. So Ra1 plus Ra2 up to Ram, this is nothing but the set of all. So basically, this R can be any Ri. Ri. So this is just summation Ri Ai, Ri in R, any element. So with this Ra, we call it as a submodule generated by A, by the set A. So an equation R1A1 up to Rn equal to 0 is called relation. So now let us study what are called finitely generated modules. So a submodule n of M, possibly n equal to M, is finitely generated if there is some finite subset A of M such that n is equal to Ra. That is, if n is finite, n is generated by some finite subset. So basically, if n is finitely generated, if you can write n to be Ra1 plus Ra2 plus up to Ran for some ai in ai fixed, okay, ai fixed in M. If n is not finitely generated, then no finite subset can generate n, and n is sometimes called infinitely generated set. Now, what does finitely generated mean? Any element of n can be written as an R linear combination of the elements of A. So here I want to make a remark that a submodule n can be generated by many different generating sets. For instance, n itself always generates n. For example, Rn is nothing but n, because any element here is contained here, and any element here can be written as 1 times that element. And finally, one more definition, that is direct products. So again, we want to make sense of product of some modules. And how do we do that? It's nothing but if you have M1 up to Mk, a collection of R modules, then the collection of K tuples, that is M1, M2 up to Mk, where each Mi is an element of capital Mi, with addition and action defined component wise, is called direct products. So M1 up to Mk plus M1 dash up to Mk dash, this is defined in this module by M1 plus M1 dash up to Mk plus Mk dash. And similarly, R times M1 up to Mk is defined as Rm1, so Rm1 up to Rmk. So this would make M1 cross M2 cross Mk to be a module. The direct product of a collection of modules is again a module. So you can verify the definitions, the axioms, the three axioms, and it will satisfy them. The direct product of M1 up to Mk is also called as external direct sum, and is sometimes denoted as M1 M1 plus M2 plus Mk. One can write Rn to be isomorphic to R cross R cross R n times. Why? Because this is directly by definition. So Rn is nothing but the set of all n tuples with elements in R, and this by definition, this is nothing but uh, I mean this by definition is R cross R cross R. So one can have equality also here instead of being isomorphic. So now let us study some a basic type of module. So we want to ask the question: does every module have a basis? Does every module have a basis? Let's see. So first of all, we need to make sense of a basis. What is a basis? So, and we also haven't thought about what is the definition of linear independence. So let V be a R module and A be some subset of V. We call A an independent set if whenever a linear combination R1 plus V, R1 V1 plus up to Rn Vn is 0 with Ri in R and Vi in A. All of the coefficients of Ri should be 0. That means sigma Ri Vi equal to 0 should imply Ri equal to 0. So whenever these are elements from A, so we call A an independent set. So in you would have seen a linear independence of a list of vectors, but here we are taking any set. So we can make sense of any set an independent set. We call A a basis if A is independent and A generates V. So A is independent is by this definition, and A generates V means V equals to Ra. So any element of V can be written as finite linear combination of elements of A. If A is a finite set, we say A is a finite basis. I mean, continuing the last definition, if we have A is a basis and A is a finite set, then we call A a finite basis. The cardinality of A is called the rank of V. So let's unpack the definition. So what does it mean for A to be a basis? It means that first of all, it means two things. What does A being a basis mean? Firstly, it means that A is linearly independent. A is linearly independent, and Ra equals to V. So what does Ra equal to V mean? Every non-zero element X of V, there exists. Let's see why this unique came. uh, there exists non-zero elements R1 up to Rn and A1 up to An such that X equal to R1 A1 plus R2 A2 up to Rn An. So this the existence of Ri AIs such that X is a linear combination of Ri AIs is nothing but this is due to Ra equals to V. And why it should be unique? Because if you write, let's say if you write X as 2 in two ways, sigma Ri AI as well as sigma Rj Bj, let's say, that would mean you can just that would mean that you would have a relation like this R1 A1 plus up to Rn An, and then you can subtract here R, okay, let's take dash. So R1 dash B1 minus up to Rn dash Bn, and this would be 0. So this, by the independence, this would imply that each Ri needs to be 0. So that means X would be 0. So we started with a non-zero element. So every non-zero element can be written uniquely as a finite linear R linear combination of the of elements from A. So what is a free module? So we are talking about free modules. We talked about free modules of rank n. So let's see what free means. We call an R module free if it has a finite basis. That means you have some finite set A1 up to An such that they are independent as well as Ra equals to V. One of the main examples of free modules is Rn. What would be the basis for Rn? So if one sets ei to be the n tuple with all zeros except at ith position and one at that ith position, then it is easy to see that a equal to e1 up to en is linearly independent as well as it generates Rn. So basically, what I'm telling is that ei equal to all zeros, one at ith position, again zeros, all zeros. So any element in Rn, let's say R1 up to Rn, can be written as R1 times 1 0 0 0 and so on up to Rn times 0 0 0 up to 1. So basically R1 E1 plus up to Rn En. So one has this. Any element of Rn is just a finite linear combination of E1 up to En, and you can see that this is linearly independent because if you have, let's say, x1 E1 plus xn En to be equal to 0, what does that mean? That just means x1 up to xn is 0. Uh, okay, I have to make sure what this 0 means. This is just 0 0 0. since it's an element of Rn. So x1 up to xn is also 0, 0, 0. So this implies each xi is 0. Belonging to R, xi is 0. So this would be a basis. So we can do similar steps, and we can try to characterize all free modules. So this is the characterization we are going to prove. If V is a free R module, yeah, V is a free module if and only if V is isomorphic to Rn. That means the examples we saw, that is Rn, these are the only free modules up to isomorphism. Let's see. So we have two directions here, and the first will prove the if only if direction. uh, let's suppose that a equal to v1 up to vn is a basis. Now you consider the map Rn to V. Now this takes any n tuple x1 up to xn xi in R. So this is taken to x1 v1 plus x2 v2 up to xn vn. In particular, where is 1 comma 0 comma 0 taken to? It is just taken to v1. That is, e1 is taken to v1, e2 is taken to v2, and so on. En is taken to vn. So let's see if this makes an isomorphism. Yeah. So now, first of all, it's a homomorphism. Why? If I denote this map by phi, then phi of I'll denote this whole by x vector. So phi of x plus y is equal to, clearly this is the this is nothing but xi plus yi vi, and due to the module axioms xi vi plus yi vi, and this is phi of x plus phi of y, right? So this is clearly a linear map. Again, you can check phi of r x vector equal to r times phi of x vector, because this would be rx1 rx2 rxn in the place of x1 x2 up to xn, and you can just take out r. Now again, what do we have? Can What's the image? So obviously image of phi is just equals to v, right? Because we already why this is because ra equals to v. Any element of v can be written as r1a1 up to rn an. So phi of r1 up to rn would give us v. And is it injective? So let's suppose that x belongs to kernel of phi. That is, phi of x is equal to 0. Now what happens? x1 v1 plus up to xn vn equals to 0. Now since v1 up to vn were independent, this would imply that x1 equals to x2 equals to each xi is 0. So note that the only place we have used the linear independence of a is in proving the injectivity of phi. So what have we proved? So we have proved that phi is an isomorphism. This would mean that Rn is isomorphic to A, V. On the other hand, to prove the if condition, let's suppose V is isomorphic to Rn. Now there exists an isomorphism F from Rn to V. Now you consider Fe1, Fe2 up to Fen. So is this a basis? Let's see. So we need to prove two things. First of all, linear independence. F of x1 f of e1 up to xn f of en. Let's suppose this is 0. So since f is an isomorphism, this means that you can just take this inside, since these are all ring elements. F x1 e1 up to f xn en, this is 0. Now since f is an isomorphism, it respects addition, so you can have all of these in f. So again, since f is an isomorphism, it is injective. In particular, this means that x1 e1 up to xn en belongs to kernel, that is, it is 0. But note that e1 up to en, they are independent, right? So basically, what does this mean? This means x1 x2 xn is 0. So again, this 0, this is a element of Rn, right? So this is actually, you can call it as 0 vector. So this in particular means each xi is 0. And further, does this set generate the whole of V? Uh, to see that, let's take V in V. Now, since this is an isomorphism, in particular it is surjective. So there exists some x such that this is equals to V. That, what does that mean? That so you can write x as, so this x belongs to Rn. So you can write that as x1 E1 plus up to xn En equals to V. So this would imply you can write it as x1 f of E1 up to xn f of En. So this would prove that R f of E1 plus R f of En is actually V. So this set generates V as well as it is linearly independent and it is finite. So V is a free module since V has a finite basis set. So this proves the theorem. So now we have characterized all free modules, that is all modules which have finite basis set. So now let's go and see whether this is all. So now again we impose three conditions for the modules that have basis. One is finite basis. It should have finite. It should have a basis. Two things, right? And in basis we have two things. One is a generation, Ra equal to V, and the second thing is linearly independent. So it's basically three conditions we have imposed on the module. Okay. So let's see whether let's talk about this now. The free modules behave very much like vector spaces, since we already proved that V is isomorphic to Rn, and you can derive many theorems in vector spaces. You can just transfer them to free modules, but it turns out that most modules do not have a basis because we impose three big conditions. I mean, many modules need not have that condition. The modules that have finite basis are all isomorphic to Rn, but this is a very narrow class of modules. So firstly, the basis can be infinite. Why? Here is an example. Consider the R module. You consider all the infinite tuple R1 up to R2 up to till infinity, where each Ri belongs to R, and Rn is 0 for all but finitely many n. So what does this mean? Basically, you have let's say R1, R2, and so on. After some point, you have 0, 0, 0, 0, 0, or I mean, just till infinity. So Rn, so after some point, Rn equal to 0 for all n greater than n. So this is the set we are defining M. Okay. So what the claim is that A equal to E1 up to E2 up to infinity. This set is an infinite basis for the module. So let's quickly check if check this. So again, what is the definition of E1? E1 is not, so E1 here means 1 at the first position and 0 all. And EI means just 0 at the ith position and the rest are still again sorry, one at the ith position and the rest all are 0. Okay. So firstly, these are linearly independent. I mean, the if you take a finitely many of them, let's say x no, I must say xi1 up to xin. If you take finitely of them and equate to the zero vector, what does this mean? This is a infinite tuple where you have x1 at the i1th position, and again maybe some zeros, x2 at the i2th position and some zeros maybe, and xn at the in position, and the rest all are zero. So 0, 0, 0 here. So since we are equating to 0, this clearly means each xi is 0. So this is a linearly independent set. And further, given any element v in M, so you only have finitely many of them non-zero. Let's say you have some y1 over here and y2 over here and yn over here, and the rest all are zeros. So only finitely many of them are non-zero. So you can see that this will be a linear combination of some EIs. So if this is J1th position, J2th position, and let's say Jnth position, then this will be equal to y1 ej1, y2 ej2, and so on. So in order to ensure this, we are restricted this condition that Rn is 0 for all but finitely many n. So this clearly proves that A is an infinite basis, is a basis, but A is actually an infinite set, and you can't find a finite set. For example, you just take up some finite vectors, then I can go far away and I can place some values, like in the far away place values, to get a contradiction. So you can't have a finite basis in this set. In particular, this module is not free. And so this means that, let's say, so so again, let's recap what are finitely generated modules. You have some finite set A, and you have some ring R acting on the set A to get V. So this A is actually a finite set. So the question is, are finitely generated modules even free? That means you have some, in the language of linear algebra, you have some n vectors that span V. Can you find a basis out of these vectors, or is there some finite basis? So in linear algebra, you would have, if you're familiar, you would have seen some theorem that whenever n vectors span a finite dimensional vector space, you can reduce that to a basis. But this doesn't work in modules. So consider the module M. It is generated by two elements, 2 comma x. So again, Zx is the ring of all polynomials with integers in with coefficients in integers, and M. What is M? It is just 2 times p of x plus x times q of x, where pq belong to Zx. Right. So this is a module, since it is an ideal of Zx. So clearly, we have a generating set A equal to 2 comma x. So so 2 times an element from the ring Zx, x times some element from the ring. So this would make all of A. But now, if you have, let's say, A and B are any two elements, both are not zero, then AB cannot be an independent set. Why? Because you have A, you multiply B, and you have B and you multiply minus A, you'll get 0. So you have a non-trivial relation between these two elements. Again, this belongs to the ring. The ring is Zx. Right. So no two elements are linearly independent. So if you want linear independence between elements, you can have at most one element. But you can check that this module can never be generated by one element. You can think of it. So you can't make one polynomial one polynomial, one ideal which has both 2 and x. So M cannot be generated by a single element. So what the point of all this thing is, like all this discussion, is that M is not free. So M is not free because why is M not free? I mean, M is finitely generated. It is, so M is Ra, where A is just 2 comma x, but you can't find a basis for it. So basically, there are modules which are not free but are finitely generated. So let's see if we can try to characterize. So let's turn to the case when we do not have a finite basis, but we have a finite set A that generates R. So all we can say at this point is V equals to Ra. If suppose, since A is finite, let's suppose A is V1 up to Vn, then what do we know at this point? V equal to R V1 plus up to R Vn. So what happens if we consider the map we used in proving last theorem? The map was phi, and that is from that takes x1 up to xn to n tuple to x1 v1 up to xn vn. In particular, it takes ei to vi. So what does happen? Again, I told you in the end of the last proof that we are using the linear independence only to prove its injectivity. So we already have that this map is a homomorphism as well as it is surjective. So why is it surjective? Because the set A generates V. So therefore we already have a very basic characterization that if V is a finitely generated module, then there exists a surjective map from some Rm to V. And in this case, by first isomorphism theorem, you have Rm over kernel phi is isomorphic to V. So like, can we improve this? So what can we say about kernel phi? So we know that we know that V is finitely generated. Okay, so can you say something about this kernel phi? Is this kernel phi? So kernel phi is a submodule of Rm, right? So it's a submodule of Rm. So can you say whether it is finitely generated? So the question we are trying to ask is, in general, is a submodule of a finitely generated module again finitely generated? So again, just to remind you, in vector spaces, what we had is any subspace of a finite dimensional space is again finite dimensional. But is it true over modules? And it turns out no. See, the rings, like the fields have a lot of structure in them, but rings do not have that structure. So I mean, some modules over some nasty rings, they have this, like they are finitely generated, but they have submodules which are not at all finitely generated. We are not going to discuss those examples, but what we are going to see is, if you give this ring R some more structure, then then you can say that a submodule is also finitely generated. So let us see. Suppose R is Noetherian ring, and let V be a finitely generated R module. Then every submodule of R is finitely generated. So what is a Noetherian ring? So every ideal is of the form uh, some let's say A1 an, that is it is also, it's a finitely generated ideal. So every ideal, if R has this, if R is Noetherian ring, and if V is any finitely generated R module, then every submodule will be finitely generated. In particular, you can convert this kernel phi into the image of some matrix A. So we'll see why. We'll see the second part of the theorem later. Now let's first see how we can prove that when we give some structure to R, that is R is a Noetherian ring, then is this true? I'm sorry. Yeah. So the matrix A that came in the second part is called as presentation matrix. Now let's see the proof. So the proof is quite intuitive. So we want, like, we are using induction, but so what we want to prove is some statement about a module V. This is finitely generated, and we already have a surjective map that goes to V. So it is like, what we do is that we prove the theorem about Rm, and then we send that like we try to show that this statement is also true on V. So the first statement is that show that every submodule of Rn is finitely generated. Note that Rn is finitely generated. So we want to show that theorem is true for Rn first. So the way we go is induction on n. So for n equal to 1, the claim is true, right? Because any submodule of R is just an ideal of R, and that ideal is finitely generated because R is Noetherian. So induction step, we want to assume that every submodule of Rn minus 1 is finitely generated. Now let's see for Rn. So you construct pi, a map from Rn to Rn minus 1. What does it do? It just skips the last component. For example, what does pi of x1 up to xn do? So this just takes x1 up to xn to x1 up to xn minus 1. So clearly this map is surjective. And this map is also a linear map. So we had that, like we had assumed that theorem is true for here, and we want to show that it is true here. So what we do, so what's the kernel of this map? The kernel is nothing but R, and the image is Rn minus 1. Again, let's see kernel pi. If V belongs to kernel pi, if and only if, let's say V is nothing but x1 up to xn. So it belongs to kernel pi if and only if pi of x1 up to xn is 0. So this is if and only if x1 up to xn minus 1 is 0 by the definition of pi. And again 0 vector. So this is if and only if each each x1 up to xn minus 1 is 0. So so the kernel, sorry, did I miss something? Yeah, it drops the last component. So yeah, so therefore what does this mean? So it belongs to, so x1 up to xn, So a vector V belongs to kernel pi if and only if its last component can be anything. All first n minus 1 components are 0. So the last component has the freedom. So this is the last component can be any element in R. So this is isomorphic to R, right? So I'm sorry. So the image is it is surjective map, and these are both modules whose submodules are finitely generated. Why? Because by n is equal to 1 case, R is finitely generated and every submodule is finitely generated. By induction step, Rn minus 1 is finitely generated and every submodule of Rn minus 1 is finitely generated. So if now what we do is we go to the submodule of Rn. So let I be a submodule of Rn. Now you restrict the map pi which went from which was defined on Rn to the I. So this is a homomorphism first of all, and the kernel and ideal are both finitely generated. Why? Because kernel of pi I is nothing but kernel of pi intersection I. And so since kernel of pi is finitely generated, kernel of pi intersection I is finitely generated, and image of pi I is a submodule of Rn minus 1. So again, by induction step, Rn minus every submodule of Rn minus 1 was finitely generated. So this image is also finitely generated. So now what do we have? We have a map. So we have a map pi I that goes from I to Rn minus 1, and and we have kernel I is kernel pi restricted to I finitely generated, image pi restricted to I finitely generated. Okay. So if in general what happens is if you have a homomorphism between two modules, and if both kernel and image are finitely generated, then this module V here is finitely generated. And to show this, I mean, if we show this, we are done, right? So we have pi restricted to I from I to Rn minus 1. This map has both kernel and image finitely generated. So this ideal I is finitely generated. So this would prove that every ideal of Rn is finitely generated. So let's prove this. So now why is this true? So let's suppose kernel is k1r plus k2r up to krr because it is finitely generated. And let's suppose that image of phi is phi v1r up to phi vnr. Again, these are some elements in the image of phi and they generate the image im phi. Then what can we say? So let's suppose w is in V. Then phi of w, this belongs to image of phi. Okay. So by the assumption here, so this is equal to some ring element R1 times phi 1 plus R2 times phi 2 up to Rn times phi n, right? So now you can take all of these elements to the left, and you can say W minus R1 V1 up to uh, Rn Vn. This belongs to kernel of phi, because if you put phi of W minus sigma Ri Vi, what would this become? Phi of W minus sigma Ri phi of Vi, and this would be 0, right? So that means that since kernel of phi was finitely generated by elements k1 up to kr, you can write this as k1 r1 dash plus up to kn rn dash, no, kr rr dash. I am using the same notation over and over. So that means that W belongs to k1r plus k2r up to krr and v1r plus v2r up to vnr. So what does this mean? This means that so any element of V can be written as a linear combination of Ki's and Vi's. So that means K1 up to Kr, V1 up to Vn, these generate V. So what did we prove? So this is what we claimed, right? V is finitely generated. So we are done. So this proves the claim. So again, so this lemma here, so it has proved the step 1 of our proof. Now what we do, we finish the proof using surjective homomorphism. Since V was finitely generated, there exists a surjective homomorphism from Rm to V. So let's call it phi. So given a submodule, now here let us take a submodule W here. Okay. So given a submodule W, what we do is we have phi inverse here. So phi inverse of W, this is also a submodule of Rm. So since this is finitely generated, this is also finitely generated. Again, if let's say if v1 up to vn generates this, then phi inverse of v1 up to phi inverse of vn generates this. So this is finitely generated. Okay. So now so I mean, so this means that so okay, why is this finitely generated? I mean, this is I'm sorry, so this is a submodule of rm, so it is finitely generated. And let's say if v1 up to vn generate this, then phi of v1 up to phi of vn generate the submodule w. So with this surjective homomorphism, you can actually show that every submodule of v is finitely generated. So this finishes the proof. So like, what did we do with the proof? Again, so what did we do with the proof? We showed that if v is a r module, and if this r is Noetherian ring, then every submodule of v is finitely generated. So in the last theorem, what we had said is that, so if I mean, okay, v is also, v should be finitely generated module, r module. So if v is finitely generated r module, you can find a surjective homomorphism, and by first isomorphism theorem, you can say that rm over kernel of phi is isomorphic to v. So now kernel of phi is submodule of rm. Since r is r is Noetherian, this ring and this ring is finitely generated. This means that kernel phi is also finitely generated. Finitely generated, right? So that means that kernel of phi is, let's say, v1r plus v2r up to vnr. Good. So each now now you can think of, now let's now you think of, let's construct matrix A, which has v1 up to vn as its columns, right? Each column is this vector, so each vi is, this belongs to rm, right? So therefore it has m components, and you just lay out those components and form the matrix A. Then you see that any element of kernel phi is actually equal to A times some vector in rm. So you can make kernel of phi equal to A times rm. Why? Because let's say if a do I have space? Yeah, I'll just write here. So if, let's say, kernel of phi, some element v belonging to kernel of phi, you write it as v1 r1 plus v2 r2 up to vn rn. So these are vectors in rm. So what you can easily write this also as v1 up to vn, and here you lay out r1 r2 rn. So if you just do this, so if you just carry out the multiplication here with the between these two matrices, you'll easily get this, and which will be equal to v. So therefore, so what do we have? So we have that for any finitely generated module v, we have rm over a rn is isomorphic to v. And so we are able to find this nice form for any finitely generated module. So we'll use this form for proving the fundamental theorem. So but in the meanwhile, let's try to solve let's have a derail a bit, and let's try to solve equations over integers. So first of all, again, in order to solve ax equal to b, so as you're familiar with linear algebra, we used row operations and column operations. So in row operations, you had three operations. You could interchange rows, you could multiply some non-zero number, and you could put, in the place of ri, you could put ri plus krj for some row. So similarly, we want to define row operations in over integers also. So the first row operation is, you can replace ri with ri plus krj, and the corresponding column operation is ci with ci plus k dash rj. Again, k and k dash are okay, I'll put any integers, not only greater than 0, any integers, right? So the second operation is, you can multiply a row only by -1. No other element is allowed. Okay, so you can't multiply by 2 3, so you can only multiply by -1. And the third row operation is you can interchange two rows or you can interchange two columns. Now, let's try these examples on this matrix 1, 2, 3, 4, 6, 6. So, firstly, so what can we do in order to simplify it? So, we have four here and 1 here. You can have, you can replace R2 with R2 minus 4R1, right? So, what would this do? We have 4 minus 4. This would yeah, so this would replace here it would come 0. Now 6 minus 4 times 2, 8, so that is minus 2. 6 minus 4 times 3, that is minus 6 over here, right? And the rest are the same, 1, 2, 3. Good. So now I want, let's simplify a bit more. Let's see. So you can, in the place of column 2, let's put column 2 minus 2 times column 1, right? So what does that become? 1, 0, let it be like that. 2 minus 2, that would be, make it 0, and minus 2 would remain the same. Again, since there is 3 here and 1 here, so C3, you can replace it with C3 minus 3C1, and that would make 0 here and minus 6 here, right? And finally, again you have minus 2 here and minus 6 here, so you can turn C3 to C3 minus 3C2, right? Again, row operation 1. So that would zero out this whole column, 0, 0, 0, minus 2, 0, 1. And finally you can turn R2 to minus R2, and that would make 1, 2, 0, 0. So, like, what did we do? We turned this complicated looking matrix and we turned it into 1 and 2. So, in general, let's say you have some matrix A, right? So, we want to think whether is it possible is it possible to use these 3 row operations and convert it into some diagonal. Only diagonal elements you have non-zero and 0, 0. We may not have full diagonal, and we may have some zeros over here also and some zeros below also. So we have some non-zero elements in the diagonal like this matrix, and it turns out that you can, and that leads us to the what is called as normal form. So given a matrix A, and it can be any m cross n, no need of square matrix, there exists P and Q, and P belongs to GL and Z. This just means that it is invertible and it is n cross n. So P is an n cross n invertible matrix, and Q is n cross n m cross n invertible matrix, such that a da- a dash equal to Q inverse AP equal to D1 up to DK, 0, 0 everywhere else. And here you have more one more condition, like one more interesting thing you can put: each di should divide di plus 1. So you have these divisibility relations over here. So again, this we had here also, 1 divided 2. So this is true in general also, and we are going to prove this theorem. So the way we prove is, we'll try to give an algorithmic proof. So do this, and you will get it. So how do we start? So the first step is, by permuting the rows and columns, what we do is we move a non-zero entry, okay, a non-zero entry with smallest absolute value to the upper left corner. So I mean, let's say you have some smallest entry, okay. So then what you do is you'll push this to the first column, and then you can push it to the first row also, and you can make it positive if necessary by multiplying the whole row with minus 1. So therefore we call such an element a11. Now what do we do is we clear out the first column. So how do we do this? So basically this is the smallest element, a11. So whatever element ai1 is here, it will be bigger than a11, right? So now you can consider the row operation ri. You can replace it with ri. Okay, so the first thing what we are going to do is, Z is a Euclidean domain. So you can divide it. So you can write AI1 as A11Q plus R. Okay, so therefore I'll write AI1 as A11Q plus R. So now what you can do is Ri, you can replace it with Ri minus Q times R1. So then this element over here, ai1, it will turn into it will turn into directly r, right? So because you had a11 q plus r minus q times a11, so you get r. So now this r, by Euclid division lemma, this r will be less than a11. So what did we do? So we found out a new element which is less than a11. So therefore it is time that this goes to the upper left corner. So we move r to the upper left corner, that is smaller than a11. So what did we achieve? So we had a11, and now we found some r which is less than a11. Now again you would perform it to some other column, let's some other element in the first column, and you get some r dash, which would be again less than r. You can keep on doing it, but you can't keep on doing it infinitely many times because we have integers, and this process is going to end. Let's say if it gets to 1, again all of these are again greater than 0. If it gets to 0, yes. So you can perform this step over and over and clear out the whole first column. Now what you do is you turn to again integer, the first column, first row, and you will again clear out those also. So finally, after clearing out all of those, you are left with one a11 dash. All of these are 0. Again, all of these are 0, and you have a submatrix M, the rest of it. Now, our next step involves checking if each element in M is divisible by a11 dash. So why do we check this? Is because we need the divisibility relation d1 divides d2 divides up to dk. So if all the elements in M are divisible by a11 dash, you can perform step 1 and step 2 to M. So otherwise, what would we do? So so we check if every entry of submatrix M is divisible by the entry at upper left corner. If yes, we perform steps 1 and 2 on M. Or let's say if entry B of M is not divisible by a11. What we do, we add the column of A that contains B to the column 1. So then what happens is you have a11 dash, you add this column to column 1. So you have B here, and here you have the submatrix M. The rest of all are 0. Good. So now this produces I'm sorry, not a column. This produces this produces a column. The first column has another entry other than a11 dash, and again this will send you back to send you back to step 1, step 2. Yeah. So so by this way we go back to step 2, and again clear out that B, whatever comes into the first column. And so in this way we do this again and again, and until we get a submatrix M such that every entry of that submatrix is divisible by the entry at upper left corner. Once you do this, uh, uh, once you do this again, you go back to steps. You go to step 1 and 2, and you apply that to submatrix M, and you can keep on doing this to get the desired form again. So why Q and P and these divisible relations are true? Because at each step you are performing row operations, right? So every so every row operation will produce some, let's say some matrix, some elementary matrices will be multiplied to left as well as multiplied to right, and so on. So the product of all such elementary matrices that correspond to the row and column operations, that will give you this Q and P. And finally, why these divisibility relations? Because we ensure that like after steps 1 and 2, we ensure that every element of the submatrix is divisible by di. I hope this is clear why this theorem is true. So this was all for Z, right? Good. So what was special about Z? With some more work, we can show that the last theorem as for matrix is actually true over any PID. So what do I mean by this? So if A is a M cross N matrix over PID R, again, what is again, to just remind you, PID means every ideal is principal ideal of the form A. Okay, so if the ring R is a PID and A is a matrix over the ring R, then there exists P and Q invertible. So again, this is M cross N, this will be M cross M, and this will be N cross N. So these both are invertible, and this will have the form d1 up to dk. Okay, d1 up to dk with the rest everything 0, and even all the elements here and here are 0, and the diagonal element satisfy di divides di plus 1 again. Or the PID, you can have the concept of divisibility, and this is called as Smith normal form of the matrix A. And these elements di, you can prove that they're unique up to multiplication by a unit. So I'm not going to prove this Smith normal form here, but I'm going to use it for the fundamental theorem. Good. So solving equations again, our main motivation was to solve equations. So suppose you want to solve this homogeneous equation Ax equal to 0. A is a M cross N matrix over R with entries in R. So what do you do? So again, by the discussion we did, you can convert A into a very simple form with many zeros over it. So using the row and column operations, you will turn A into A prime Q inverse AP, which is of the form again D1 up to dk, the rest all zeros. Good. So now you observe that A prime of X equal to 0 if and only if X is the first all of them are zeros and the rest are any elements. And again, this is very easy to see. If you have dk d1 up to dk and the rest all are zeros over here, over here, over here, and you have x1 up to xn, right? So what does this give? This will give you d1 x1 up to dk xk, and again the rest all are zeros, right? So you are equating this with the zero vector, right? So that, what does that mean? That means that each x1 up to xk should be a 0, each x1 equal to x2 equal to xk should be 0, and the rest after k plus 1 they can be anything. So this gives you x equal to any the first k of them 0 and the rest can be anything, right? So once you solve it for a simpler matrix, you can okay, so okay, you can convert it into you can make the solution, find a solution for the general matrix. How do you do that? So you have A prime x equal to 0. Okay, let's start with Ax equal to 0. This is if and only if you can multiply q inverse Ax equal to 0. Good. So now what you do is you introduce a p here, p and p inverse, right? P inverse will be 1, identity matrix over R. So you can take this again by associativity. So this would be A prime p inverse x. In the place of p inverse x, let me temporarily put y equal to 0, right? And we already solved this before. So this becomes what? This becomes y equal to 0 0, first all zeros, and then you have any yk plus 1 up to yn. But this was what I substituted p inverse x. So this will give you the solution x equal to p times the matrix p you get times 0 0 0 0 up to yk plus 1 and yn. So this would give the solution for the homogeneous equation. So that's what I have written here. So in order to solve Ax equal to b, one can follow similar steps. So therefore, the Smith normal form decomposition of A will help us in solving equations over integers. So finally, we come to the main theorem of the talk, that is fundamental theorem. So basically, we started with the problem of characterizing all the finitely generated modules, and the last where we stopped at was we said that there exists integers m and n and a matrix A such that Rm over Arn is isomorphic to V, right? So I hope this is clear till now. Now we have this matrix A, and we saw that you can simplify the matrix using some row and column operations. So let's see if we can try that. So before that, I like to state the theorem, and there are many forms of fundamental theorem, and we are going to see some forms, and the form that we are going to see now is invariant factor form. So again, we want to take a well-behaved ring. So let R be a PID, principal ideal domain. Now, and let V be a finitely generated module. This is what we want to study. So this theorem says that V would be isomorphic to R to the power R, and this is the external direct sum, and R over D1, R over D2 up to R over dk. So this says that any finitely generated module is a direct external direct sum of one free module, this is a free module, and some cyclic modules. But further it says that the r is some greater than or equal to 0, and these are non-zero elements, and d1 up to dk are elements of r such that they have the divisibility relation d1 divides d2 divides dk, right? So again, why they are not units? Again, because if they were unit, then the ideal generated by that would be r, and r over r is nothing but just that doesn't make sense. So we make we the condition is that they are not units. Good. So before we do the proof, we want to have some intuition on what the theorem actually says. So when R is a PID, the theorem says that if V is a finitely generated module, then V is isomorphic to a direct sum of finitely many cyclic modules and one free module. Indeed, you can prove that, which we are not going to do here. The decomposition given in the theorem is actually unique, but we won't prove here. The DIs that come in the fundamental theorem are called as invariant factors of V. The invariant factors together with R completely determine the module of V. Yes, because the only things that are coming here is this di, d1, d2, dk, and this r. So if you are given that, you can completely determine the whole module of V via isomorphism, up to an isomorphism, right? So the theorem also says that you can write every element V in V as x1 up to xr and some a1 bar up to a1 ak bar. Okay, so these are elements in R and these are elements in R over di. Good. So this is because you write r to the power r as r times, and then the rest are r over d1 up to r over dk. Okay, so now let's go to the proof. So the proof, we have done much of the hard work already. Uh, as R is a PID and R is a Noetherian ring, right? We know there exists M and N such that R to the power M over ARN is isomorphic to V, where A is a M cross N matrix over R. And we also know that since R is a PID, we can write A in a Smith normal form. So there exists invertible P and Q, P n cross N, Q m cross M, such that Q inverse AP is of this diagonal form, where the diagonal elements also satisfy di plus 1. So you would have already you would be trying to guess that these are the di's that are going to come there. So but how do we convert it? So in order to convert this these di's to come there, we need to simplify this whole equation, that this whole isomorphism that we got. So in order to simplify, let's try to see if by replacing A with Q inverse A, we get the same module. So consider this isomorphism, let's call it phi, that goes from Rm over Arn to Rm over Q inverse Arn. So basically you're considering, so how do I define this? So I'll consider x plus Arn, a left coset. I'll map it to another left coset of left coset inside this. So I'll map x to Q inverse x. So x plus ARN goes to Q inverse x plus Q inverse ARN. Now, firstly, you can easily check that this is a linear map. So I'll just do it very quickly. So if I have x plus ARN plus R times, R times y plus ARN, then you clearly have this is x plus ry inside phi ARN, and uh, this is nothing but Q inverse x plus ry plus Q inverse ARN. This is due to the definition of phi. Right. So this is equal to Q inverse x plus Q inverse y, which is nothing but phi of x plus ARN plus phi of y plus ARN. And you can here you have r times Q inverse y, so you have r outside. So this would prove that phi is indeed linear. And why is phi surjective? Clearly, you have, let's say you have some modules Q inverse ARN in the RHS. Now what you do, you would map Qy plus ARN. So where would this go? So Q inverse times Qy is just y. So y plus ARN. So this implies that phi is actually surjective. And why is phi injective? Let's suppose that some element x plus ARN is going to 0 plus Q inverse ARN. the zero element in RHS. So this is equal to Q inverse X plus Q inverse ARN equal to 0 plus Q inverse ARN. So this means that Q inverse ARN, Q inverse X belongs to Q inverse ARN. In particular, what this means is that you can have some element such that this is equal to element Y such that Q inverse AY equal to Q inverse X. And this would give, multiplying Q both sides, this would give AY equal to X. So that means, this means that, what does this mean? This means X plus ARN is just 0 plus ARN because X is already equal to AY for some Y. So, right? So this means that this element is trivial element. So therefore the kernel is just, so what did we prove? So we proved that kernel of phi is just equal to 0 plus ARN. So this map is indeed an isomorphism. So what have we proved? We proved that Rm over ARN is isomorphic to Q inverse Rm over Q inverse ARN. So now what you do is, now you would write Q inverse ARN, you would write it as Q inverse AP times P inverse Rn. And you know, since P is an invertible matrix, it would be surjective. So P inverse Rn is nothing but Rn. Since the image of, the image P inverse would be a map from Rn to Rn, right? The image would be, since it is surjective because it is invertible, the image would be whole of Rn. So you can write this isomorphism as well. Good. So this gives us Rm over A dash Rn. So, and A dash, you know, is of very simple form, d1 up to dk, and the rest are zeros. Now what you can do is, you can recognize A prime Rn as direct sum of d1 d2 up to dk. This is because, again this is very simple. Any element of A prime Rn is d1 x1 d2 x2 up to dk xk, and a bunch of zeros at the end. So this, this is nothing but, this is nothing but, by the definition of external direct product, as we saw, this just belongs to d1 cross d2. So what we did is to recognize A prime Rn as d1 cross d2 cross d2 d3 up to dk. So basically what we did is to write this. So this would rewrite the denominator, and similarly we would rewrite the numerator. Okay, so how would we rewrite numerator? We want to write it as r to the power r cross r cross r cross r up to r, and this is m minus k times, sorry, m minus r times, right? So that means that we have this quotient module equal to a quotient of a direct product and another external direct sum or direct product, whatever you can call. So, and if I would write a trivial module here and put and make it a direct sum. Now if I could just split this and so on up to this, since this is just k times, right? So if I could split, I would be done, right? Because then I mean, if I could split it like this, then I would be done. I am showing V is isomorphic to r to the power r plus direct sum of some cyclic modules, and this last step will be justified in the next lemma. So the lemma says that if if A1 up to AN are R modules and BIs are submodules, then you can actually split it. Like given that the number of given that you have n modules over n modules, so you can split it. So like this looks like some symmetry, or this looks like, how does one prove it? It's actually easy. You just consider this map. So basically this map goes from A1 direct sum A2 direct sum AN. This map goes from here to the RHS, the right hand side over here. So what we do, we take x1 cross x1 up to xn. You can identify this as a direct product. So you take x1 up to xn and map it to x1 plus b1 up to xn plus bn. So what is the kernel? So this is clearly clearly a linear map. What would be the kernel of this map if I call this phi? So x, let's say x vector belong to kernel phi if and only if, what do we have? X1 plus b1 comma xn plus bn. This is a zero element. The zero element in the RHS is nothing but 0 plus b1 up to 0 plus bn, right? So what does this mean?
if and only if each xi plus bi is equal to 0 plus bi. So this is if and only if each xi belongs to bi. But in so okay, so this is if and only if. What does that mean? So that means x1 up to xn belongs to b1 cross b2 across bn. So this is again, you can identify this with a direct sum. So 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 what do we have? So for this isomorphism, okay, the above statement is just the first isomorphism theorem. You have the image here and you have the kernel here. So therefore, with the help of this lemma, we have proved the fundamental theorem of finitely generated modules. So basically, it tries to characterize every single every finitely generated module. So now let's look at one more form, and we are not going to prove this form. Like it follows directly from the last form. So one has, using the assumptions before, one has v isomorphic to r to the power r, and here you have instead of d1 up to dk's, you have prime powers p1 alpha 1, p2 alpha 2, pn alpha l. So these pi's need not be in any way distinct. So they are just primes in r. Again, note that r was a PID. So R is actually UFD. So you have a concept of primes in R. So in order to prove this, you need what is known as Chinese remainder theorem. And this says that given A and B, whose GCD is 1, you can always write R over AB as R over A cross R over B, or the direct sum of R over A and R over B. So let's use the proof, like see the proof with an example. If you have V, if you have V isomorphic to Z, direct sum Z over 6Z and Z over 18Z, Z over 54Z. I mean, if this is the invariant factor form, right? So these are, again, I think I missed. So these are called as invariant factors. Invariant factors. So how do you do that? So first of all, Z over 6Z, you would write it as Z over 2Z cross Z over 3Z. Similarly, you would write Z over 18Z. Again, this is by Chinese remainder theorem, CRT. So 18Z, 18 is nothing but 6 times 3, right? Or you can write 2 times 3 square, and each of these is has are co-prime. So this is Z over 2Z, Z over 3 square Z. And similarly, Z over 54Z, you would write this as isomorphic to, again, this is 9 times 6, so that is 3 to the 3 cube times 2, right? So you would write it as Z times 3 cube times 3 cube Z, direct sum Z over 2Z. So just place this each of these isomorphisms in its place, and you will see the you will see the prime, uh, the second form. So that is Z cross, you have Z over 2Z from here, and you have another and one more. So Z over 2Z, Z over 2Z, and Z over 3Z, Z over 3 square Z, and Z over 3 cube Z. So each is a prime in Z. So this will, again, you can extend this proof to general ones, and you can easily prove the last this theorem. So these, so so again, again to say, this R and each P1 alpha 1, P2 alpha 2 to PL alpha L completely determine V. Okay, so finally we'll do one application of the fundamental theorem. So if I take R to be Z, right, it's a PID. So I can apply the fundamental theorem. So if V is a finitely generated abelian group, then it is a direct sum of the cyclic subgroups CD1 C up to CDK and a free abelian group L, right? So these are nothing but, each CD1 is nothing but Z by D1Z, Z by D2Z, and so on. So you have that. So again, order of each di is greater than 1, and di divides di plus 1. Another alternate form, if v is finite, so L is of the form Z to the power R, right? So if v is finite, R has to be equal to 0. So all you have is v isomorphic to v equal to an direct sum of CD1, CD2 up to CDK. So you have that every finite abelian group is a direct sum of cyclic groups of prime powers. So this is a nice application of the fundamental theorem. I mean, although it's a result in group theory, but we have derived it using module theory. So That's all. Thank you. If you have any questions, you can ask.
I had one question that we proved that if the ring R is Noetherian, then we know that R to the power m is first of all finitely generated, and any submodule is also finitely generated. But like, so
Yes.
we proved that Noetherianness is sort of sufficient. So is
Yeah.
this also necessary, or like, do we have a example where R is not Noetherian, but this still happens that every submodule is finitely generated?
Okay. It's not necessary actually, but
Ah,
in
okay.
order to okay, so we are talking here, right? No.
Yeah.
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 So in order to, I need, okay, so I need to bring up an example where R is not Noetherian, but every submodule is finitely generated. No. Okay.
I mean, I this question just popped up. I don't know if there is an answer or not.
Yeah, maybe it is sufficient. I have V here, and I mean, I have not thought about this. So I have a surjective homomorphism from RM to V. So, um, so indeed, so this is every submodule of V is finitely generated.
Yeah.
So every submod, this means via homomorphism, every submodule of Rm is finitely generated. In particular, R is a submodule of Rm, so R has to be finitely generated.
Ah, okay. So, and since all the submodules are the
Yeah,
ideal, so we get it. Yeah, yeah, yeah,
exactly.
yeah,
So
yeah, yeah,
yeah,
yeah. Okay.
I
Thanks.
hope this works out. I mean, I have not written. I mean, I not written.
Yeah,
I
but
may
I
have
think at
done a
least,
hand
yeah,
waving. Yeah.
yeah,
So
yeah, yeah, yeah.
yeah. Any other questions? Yeah. So one last remark. So the result we saw over here, that you can recognize any fx module as a vector space and that and some linear map T. So this will be very much used to derive many properties like Jordan canonical form and rational canonical forms and so on. So all these are applications of module theory. Yeah, that's all.
Okay, then we will end the meeting here.
Thank you.
Thanks a lot. The talk was quite nice.
Ah, thanks.